So in the first part of 3.3, we got some good theorems about the Euler characteristic. One of the most important is the fact that the Euler characteristic of a surface is equal to, well, this is the definition, the number of vertices minus the number of edges plus the number of faces when you've triangulated your surface. One of the theorems was that if we have two different surfaces and take their union, then the inclusion-exclusion applies, as long as both of them are triangulated in such a way that the intersection is also triangulated. So the characteristic of the union is the characteristic of U plus the characteristic of V minus the characteristic of U union V. And again, that's called the inclusion-exclusion principle. And like I said, it shows up a lot in set theory and probability, and a lot of places in mathematics. We also saw that if we have a connected sum of G tori with B boundaries, that the Euler characteristic of this surface is 2G minus G minus B. And the connected sum of N projective planes with B boundaries is 2 minus N minus B. So we have some ways to do calculations with connected sums. We know how to make surfaces from surfaces and calculate their Euler characteristic, which in the next section we'll see is really important for classifying surfaces. And then we defined the genus of a connected sum of tori to be the number of handles. So for example, the dog bone shape has genus 2 because it has two different handles, one here and one right there. So, now continuing in this section, we define first an orientation. And an orientation of a polygonal face of a triangulated surface is a choice of one of two possible orientations on the boundary curve of the face. And a surface is orientable if we can choose orientations on all faces of a triangulation, so that if any two of them have a common edge, the faces induce opposite orientations. So that says quite a bit. So what I mean by orientations on the boundary curve of the face, it's this idea. If we have a triangle that shows up in our triangulation, an orientation will be a choice of arrows that would travel around the triangle in this direction. And we usually indicate by drawing a little curvy arrow inside the triangle. The opposite orientation, because remember we have a choice, would go in this direction, and we would draw the arrow that way. And if these two triangles are touching each other, the surface will be orientable if they have opposite orientations. So that idea of the orientations going in opposite directions can be a little bit confusing, even though we need that for the definition. But a better way to think of it may be in terms of compatible and not compatible faces. So if I have two faces that share an edge, the orientations will be compatible if they look like this, and not compatible if they look like this. Because let's follow the arrows on each and see what happens. So that's what the orientation on the edges looks like for this left face. And on the right face, it looks like this. So we have that even though this arrow inside the face, these guys look like they're going in the same direction. If you look here at this shared edge, this right face is going down and the left face is going up. So these two faces are compatible. And so this would let us make, if all of the faces in a triangulation of a surface are compatible, that means the surface is orientable. On the other hand, if we look at the arrows over here, the left one does this, and the right one does this. So even though it looks like drawing these arrows in the middle of the faces, these guys look like they're going opposite. What matters is the direction the arrows go on the common edge, and the right one goes up and to the left. Excuse me, the left face, the orientation on this edge, the common edge goes up and to the left, and on the right face, the orientation goes up and to the left. So since this common edge, they don't have opposite orientations, this means that we wouldn't be able to orient the surface. So these are not compatible. So not orientable. Okay, so now let's see an example. The torus t squared is orientable. Now, in order to show a surface is orientable, you have to find an orientation on it. So let's use the polygon, the fundamental polygon for the torus, where this edge is identified with this edge, and this edge is identified with this edge. Now we need to triangulate the torus, and this is the simplest way to do it. You just make it look like a tic-tac-toe board, and then draw your diagonals. So now the surface has been decomposed into triangles. Okay, so let's see if we can draw what the orientation would be. So I'll start like this, and in order to make this first face compatible with this face, the orientation on this face has to be like this. But to make this face compatible with this face, the orientation must be this, and so on and so forth. Now, notice when we glue these two edges together, I'll need to have this one compatible with this one. But since there are no flips, it works. Now, to get the orientation on this face, I have to look at the one that touches it and the common edge. So the orientation has to be like this, and so on and so forth. So we have an orientation on the torus. So the torus is an orientable surface. And that's going to hold for, if we do a connected sum of any tori. We'll see later that's still going to be orientable. Now let's see if we can look at one that is not orientable. So the Klein bottle, K2, is not orientable. So again, we'll look at the square that gives us the Klein bottle. And here's where we have the issue. We have the flip on the edge. Now, we have a situation where to show something is orientable, we have to just find a single orientation. But to show something is not orientable, it's not enough to, for example, make the tic-tac-toe board and draw diagonals and then draw some orientations and see what happens. That's not going to work. What we must do instead is be able to say something a little more general about the entire situation. So I'm just going to draw a more general thing that would happen whenever we're looking at the Klein bottle. And we'll see that no matter how we try to put an orientation on it, we'll always get a contradiction of the same form. So what we're going to do is, in any triangulation of the torus, of the Klein bottle, we would have a situation like this. So in any triangulation, we would have a way to go from the left side to the right side where the flip happens. So let me triangulate this diagram in any way that I want. So you can try this in different triangulations and different drawings, and this will always happen, this situation we're going to have. Whoops. Sorry about that. So let's just put an orientation in this direction. So this one has to go this way, this way, this way, this way, this way, and so on until eventually we're going to get to the other side. And this is where we run into the issue. Because now, when we make the identification of this edge with this edge, there's a flip. There's a half flip. So that means this triangle will get flipped over, which will reverse the orientation. So this edge, this face and this face will share a common edge, but they'll have the same orientation on that edge. And so that gives us the contradiction, which means that the Klein bottle is not orientable. A nice intuitive way to think of orientation is with this little drawing from the book with the little ants. And if you remember, we did the, I think it was called Torus Games, was that program that I downloaded that you could get on the Android App Store. I don't think it's available for iOS yet. But what it shows is that if we have a little creature right here crawling across the torus, notice this is the torus and this is the Klein bottle. This little ant guy is holding a flag in his right hand. If he walks across the torus and crosses an edge, he's going to show up over here again, and it's still in his right hand. If he walks and hangs a left and crosses the top, he'll show up at the bottom, but the flag is still in his right hand. On the other hand, in the Klein bottle, if he's walking with a flag in his right hand and crosses this edge, well, there's a flip, so he'll come out over here. And notice that the flag has now moved to his left hand because everything about this guy, this little two-dimensional ant, has flipped over. So he goes from here to here, and his right hand is now his left hand. So handedness only makes sense in the context of an oriented surface. Now if the guy hung a left again, he would still come out right here, and his handedness wouldn't flip around. But the problem exists because we have this flip. And if you did play that torus game with the little mouse, the hand trying to catch the cheese or the mouse or something in the maze, if you crossed an edge like this when it was set for Kleinbottle, you'll notice the left and right directions on the mouse switched, and the direction of the hand switched. So you'd have to cross it again to get everything straightened out. So it was a neat little game, and this picture, I think, illustrates the importance of orientations. And it looks like we probably either live in an oriented universe, or else we haven't got to the place where we would cross an edge like that, because our hand switching is probably something we would notice.